Have you ever wondered what makes a tiny, speeding bullet so much more dangerous than, say, a slow-moving bowling ball? Well, it's all about this thing in physics called momentum, and that's exactly what we're going to break down today.
So let's start with a little thought experiment. Picture a tennis ball absolutely zipping through the air. Now picture a heavy brick just kind of inching along. Which one do you think has more momentum? The answer might actually surprise you, and by the end of this, you'll get exactly why.
All right, here's our game plan. First, we'll get a grip on what momentum actually is. Then, we'll see what happens when things crash into each other. Collisions. We'll even look at this unbreakable law of physics, see how force fits into the picture, and finally, we'll wrap it all up with inertia and why it matters so much. Okay, so let's get right into it. What is momentum? A lot of people think it's just another word for speed, but really, it's a bit more nuanced than that. This right here is the heart of it all, and it's actually super simple. Momentum, which we use the letter P for, is just an object's mass multiplied by its velocity. That's it. So the heavier something is and the faster it's going, the more momentum it's got. Even the units, kilogram meters per second, tell you exactly what you're measuring. So it makes sense, right? If something's not moving, its velocity is zero. Anything times zero is zero. So no velocity, no momentum. Simple. But there's another piece to this puzzle hidden in that little formula. And this is a big one. Direction matters. See, velocity isn't just a number. It's not just speed. It's speed with a direction. That makes it what we call a vector. And since momentum depends on velocity, guess what? Momentum is a vector too. This is huge. It means an object zipping to the right could have positive momentum, but if it were moving left at the exact same speed, we'd say it has negative momentum. Direction is absolutely key. And this takes us right back to our little puzzle from the start. Can the tennis ball and the brick have the same momentum? You bet they can. That little tennis ball, with its tiny mass, can have the exact same momentum as that big, heavy brick, as long as the ball is moving ridiculously fast. Its huge velocity completely makes up for its small mass. Okay, now for the fun stuff. Let's see what happens to momentum when things, well, crash into each other. So when we're talking about collisions, physicists basically put them in two buckets. First, you've got your elastic collisions. Just picture two billiard balls hitting and bouncing off each other perfectly. Then you have inelastic collisions. That's more like two blobs of clay hitting and squishing together into one big blob. The really big difference between them comes down to what happens to the kinetic energy, the energy of motion. Okay, this is basically your cheat sheet for any exam question on collisions. First, you've got to state the velocities and directions of everything before and after the crash. Then, you need to say if it was elastic or inelastic. And here's the kicker. If it was inelastic, you have to explain where that lost kinetic energy went. It didn't just vanish. It probably turned into heat or the sound of the impact. All right, get ready for this because this next idea is honestly one of the biggest deals in all of physics. It applies to everything from a game of pool to planets orbiting the sun. And here it is, the law of conservation of momentum. It says this: in a closed system, the total amount of momentum you start with before something happens is the exact same amount of momentum you have after it happens. That's it. Momentum can't be created out of thin air, and it can't just disappear. It can only be passed from one object to another. Now, there is one little catch. This law works perfectly in what we call a closed system. And that's just a fancy way of saying we're in a perfect little bubble where no outside forces like friction or air resistance are messing things up. Of course, the real world isn't a perfect bubble, but in physics problems, we often pretend it is to make the calculations work. So let's see this law in action with a classic car hits a van problem. The steps are always the same. 1, figure out the total momentum of everything before the crash. 2, use the law. The total momentum after has to be the exact same number. And 3, use a bit of algebra to find whatever piece of information you're missing, like how fast the van is moving afterwards. Okay, let's look at the numbers here. Before the collision, all the momentum comes from the car, because the van is just sitting there with zero momentum. That gives us a grand total of 9,000. Now, the law of conservation tells us that after the crash, the total momentum still has to be 9,000. We know the car's new momentum, so we just pop that into our equation, do a little rearranging to solve for v, and boom, we find out the van has to be moving at 6 meters per second. See? The momentum was just transferred, not lost. Okay, so we've got a handle on momentum being conserved, but how does this link up with something we all feel every day? Force. You probably know Newton's second law as F equals ma. Well, this is just another way of looking at it, and it's actually more fundamental. It says that a force is just the rate of change of momentum. Think about it. If you want to change something's momentum, speed it up, slow it down, you have to apply a force. And the bigger the change you want, or the faster you want it to happen, the bigger the force you need. And this idea flows perfectly into Newton's third law. You've heard it a million times. For every action, there is an equal and opposite reaction. In our car crash, what that really means is the force the car slams into the van with is the exact same size as the force the van pushes back on the car with. Same force, just opposite directions. And this is the aha moment. Because the forces are equal and opposite and they happen over the exact same tiny amount of time, the change in momentum for each object has to be equal and opposite too. So, whatever momentum the car loses, the van gains that exact same amount. That's why total momentum is always conserved. It's a beautiful, self-contained system. All right, let's bring this all home by talking about one last piece of the puzzle: inertia. So what's inertia? You can basically think of it as an object's stubbornness. It's its natural tendency to just keep doing whatever it's already doing. If it's still, it wants to stay still. If it's moving, it wants to keep moving in a straight line at a constant speed. So here's the big link. Inertia is really just an object's resistance to a change in its momentum. And what determines how much inertia an object has? Its mass. The more mass something has, the more inertia it has. It's why it's way, way harder to push a car to get it moving than it is to push a shopping cart. The car has more mass, more inertia, so it fights that change in momentum a lot more. Okay, so that leaves us with one final thought. We've said over and over that momentum is conserved in a closed system. But you and I both know that if a car is just coasting down the road with the engine off, it's going to stop eventually. Its momentum drops to zero. So what gives? What external force is breaking into our perfect closed system and stealing all that momentum? Thinking about that is the perfect way to take what you've learned today to the next level. Thanks for watching.